This is a presentation and review of selected material from Mohammed Salavatapour's On Some Coloring of Graphs. The sections of the overall paper include an introduction to the chromatic sum concept, an algorithm for finding vertex strength, algorithms for specific types of graphs, and a particular example is for bipartite chain graphs, which we'll be looking at in detail, time complexity of select algorithms, and the edge chromatic sum of algorithms. So we'll begin with the concept of sum coloring. Sum coloring relies on proper vertex coloring first and foremost. And then instead of using colors such as red, green, blue, we use natural numbers, 1, 2, 3, so on and so forth. And then we sum the total sum of the colors of vertices. And we are seeking for that to be minimized against all proper colorings. And when we find the minimized coloring, we call that the chromatic sum. This concept of sum coloring was first introduced in 1987 by Sipovit and was used for the optimum cost chromatic partition problem. It was later picked up on by Eva Kubicka in her PhD thesis, and later with Kubicka, Paul Erdős, and A. Schwenk in another publication, and there have been publications since then that have dealt with the concept of sum coloring. So let's look at some simple examples of sum coloring. This graph on the left has a chromatic sum of 12. It uses two colors. The colors are 1 and 2, and again, instead of 1 and 2, we could use red and blue or green and black or whatever. And that 12 is simply 1 plus 1 plus 1 plus 1 plus 2 plus 2 plus 2 plus 2. And it uses two colors. The graph on the right uses three colors, but it has a lower chromatic sum, and this is key because the sum of 3, 2, and 6 ones is only 11. So even though it uses more colors, its chromatic sum is actually lower than that of the graph on the left. So as we delve into this material further, we're going to focus on one particular algorithm, and we need some definitions for that before we begin. One is the concept of a bipartite chain graph. And a bipartite chain graph, it's bipartite, but more specifically, in a bipartite chain graph, for each color class, the neighborhoods of the nodes in that color class can be ordered linearly with respect to inclusion. They're either subsets or equal sets. So for example, or in particular, a bipartite graph is a chain graph if for every I in j, x sub I and x sub j have neighborhoods that are subsets one of the other. So either the neighborhood of x sub I is a subset of the neighborhood of x sub j, or vice versa. So let's look at some examples of partite chain graphs. The graph on the left is bipartite. The graph on the right is tripartite. The number of partitions doesn't really matter. The concept is the same. H is a bipartite chain graph. G is tripartite. Notice that in the graph on the left, the neighborhood of V1 is a single vertex, and it's a subset of the neighborhood of V2, which is two vertices. And likewise, the neighborhood of V2 is a subset to the neighborhood of V3. The graph on the right works the same way. The neighborhood of x1 is a subset of the neighborhood of x2, and the neighborhood of x2 to that of x3, and so on and so forth. So then just a few more definitions here before we can dig into a proof. So for some bipartite chain graph, assume the partitions are x and y, and assume there are n vertices in x and m vertices in y. So we have x1 through xn and y1 through ym as our vertices of our graph. Then we're going to call g sub ij is the induced subgraph of I x vertices and j y vertices, where in particular x1 through xi and y1 through yj are the vertices of the induced subgraph. Also, we're going to assume that n minus I is greater than m minus j. We're going to assign color 2 to the remaining vertices of x where the subscript is greater than I, and we'll assign 3 to the vertices of y where the subscript is greater than j. And if that's not the case, then we're going to swap 2 and 3. So because again we're trying to minimize the chromatic sum. So if n minus I is less than or equal to m minus j, then we can swap the 2 and 3 in this definition, and we'll get the minimum value one way or the other. Then S sub ij is simply the chromatic sum over this induced subgraph. And then for that particular value of I and j, whatever that value of I and j is, that then is a proper pair if the graph Gij, which again is the induced subgraph with those two values, is a maximal independent set of G. And then S subscript min is the minimum S subscript ij over all proper pairs. And we're going to go through each of these definitions in a little more detail as we dig into the material, and we'll see some graphs, and it'll make more sense. So one of the proofs in this paper is a proof of the claim that the chromatic sum of a binary chain graph G is equal to the minimum of one of these three values, either the min S 2n plus m or n plus 2m. And again, n is simply the number of x vertices, and m is the number of y vertices. And so we're saying that the minimum sum, or the chromatic sum, for a binary chain graph is equal to one of these three. And this is what we're going to set out to prove. We're going to assume that G has an optimal coloring, first of all. We're going to assume that G contains partitions x and y because it's bipartite. We're going to we're going to do this two ways. First, we're going to assume that no vertex in partition x has color 1. And if that's the case, then all vertices in set y are going to be color 1, because we're choosing 1. We're going to definitely include 1 if we want the sum to be minimum. We definitely want to use 1, and we want 1 to cover as many vertices as possible. And if there is no vertex that's colored 1 in x, then all the vertices in y must be color 1 because it's bipartite. And then all the vertices in x must be color 2. And otherwise, if y contains no vertex that's color 1, then all the vertices in x must be color 1. And that's so the opposite would be true. Then in this case, either 2n plus m or 2m plus n is minimum, because whichever one's bigger, if m is bigger, then we'll let m be 1 and n be 2, and that would give us the smallest possible chromatic sum. And if n is bigger, then we'll in other words, there's more vertices, n. Then we will make n 1 and let m be 2, and we'll have the minimum chromatic sum. So let's look at an example of what we just said. So either 2n plus m or 2m plus n is minimum and is the chromatic sum. So again, we said let m be 1, and what we mean by that is we want m to be color 1 and n be color 2. And here's an example in this graph here of, in this case, we have the same number of vertices in each set. So in this case, they would pretty much be the same, or they would be the same. But that's not necessarily the case. So you could have more vertices in y or more vertices in x, and we just want 1 to be the color for the vertex set that's the largest. But in this case, if black is color 1 and blue is color 2, for example, Notice that all the black vertices are in X and all the non-black vertices are in Y. So again, in this graph, we're going to let black be 1 and blue be 2. And then we can calculate this out. Then n is equal to 5 and m is equal to 5. So 2m is equal to 10. So m plus 2n equals 15. And we obviously 2m plus n is also equal to 15. Then 15 is the minimum possible sum of colors. Again, using natural numbers as our colors. So 15 is the chromatic sum of this graph. So previously, we were assuming that one partition contains no color 1. Well, now let's consider that color 1 exists as at least one vertex of S and also as at least one vertex of Y. And here would be an example of that. If color 1 is red, we have red vertices in X, we have red vertices in Y, but it's still a bipartite graph, and that's what the next part of this proof is going to deal with. So then using this graph, we'll take more steps forward with this. We're going to let X sub I and Y sub j both be color 1, where I and j are the largest indices of each set colored 1. So in this case, I is going to be 3 because X sub 3 is the largest X, if you will, or the largest index of X. 3 is the largest index of X that's red. 2 is the largest index of Y that's red. Then what that means is that all the vertices from x1 to x sub I are going to be the same color. They're all going to be color 1. And likewise, all the vertices from y sub 1 through y sub j are also going to be color 1. And what that also means is that for any k less than I, the neighborhood of x sub k is going to be a subset of the neighborhood of x sub I. So if I look at x sub 1 and x sub 2, their neighborhoods are all in the neighborhood of x sub 3. And likewise for y1 and y2. Then the vertex set G sub ij, which is going to include all the vertices that are red here, all right, is going to be an independent set. And even though these vertices are in different partitions, they are not adjacent. So x sub 1, 2, and 3, and y sub 1 and 2, none of those vertices are adjacent to each other. So they are an independent set. And then the last part here, x sub I plus 1 through x sub n, which would be x4 and x5, and y sub j plus 1 through y sub m, which would be y3, y3, y4, and y5, all must be a color greater than 1. Not necessarily the same color, but they all have to be a color greater than 1. And they have to because each of those vertices, x sub 4, x sub 5, y sub 3, y sub 4, y sub 5, each of them are adjacent to a vertex that's colored 1. So they can't be color 1. Otherwise, we could just change them to color 1, but we can't because that would violate this being a bipartite graph. So then by the chain property, y sub j plus 1 through y sub m are neighbors of x sub I. And again, in this particular case, I is 3. And it turns out that y sub 3, y sub 4, and y sub 5 are all neighbors of x sub 3. And likewise, x sub I plus 1, which is x sub 4 in this case, and x sub n, which is x sub 5, are neighbors of y sub j. And again, y sub j is y sub 2 in this particular case. So x4 and x5 are both neighbors of y sub 2. Then G minus the induced subgraph G sub ij is a complete bipartite subgraph. We're going to take a look at an example of that in the next slide. And also, and this kind of follows from what we said about maximality in the previous slide, G sub ij is a maximal independent set. Then that's the red vertices because we can't add any more vertices to it. and it still retain its identity as an independent set. And then using our definitions, I and j are a proper pair. So let's look at some specific examples now using our graph for the definitions and the explanation that we just saw. In the original graph, x sub 3 is a neighbor of y sub 3, y sub 4, and y sub 5, the three blue vertices. Y sub 2 is a neighbor of x sub 4 and x sub 5, the two black vertices. Then G sub 3, 2 is a maximal independent set. And again, the 3 means the first 3 x vertices, and the 2 means the first 2 y vertices. And if we look at the induced subgraph of those 5 vertices, they share no edges. So they're an independent set. Further, we cannot add any more vertices to this set, because if we add any more vertices to the set, then we're no longer going to have a bipartite graph. So we cannot do that. So it's maximal. So G sub 3, 2 is a maximal independent set. Then let's consider G minus G sub 3, 2. We take those 5 vertices out of the original graph, and we make an induced subgraph of the original from the original with just x sub 4, x sub 5, and y sub 3, y sub 4, and y sub 5, we have a complete bipartite subgraph. And that's very apparent. In the graph in the upper right-hand corner, both of the two black vertices share edges with all 3 blue vertices. So it's a complete bipartite subgraph. So in this case, 3, 2 is a proper pair. So we're going to wrap up the proof here, the last few statements here. We're going to consider some k and L such that k is greater than I and L is greater than j. So they're greater, k and L are greater than the values of the maximum subscripts of x and y respectively, which are color 1. Then x sub k and y sub l must be different colors because they are both included in that complete bipartite induced subgraph of g minus g sub ij. So they have to be different colors because they're going to share an edge. So we're going to let x sub I plus 1 through x sub n be color 2 and y sub j plus 1 through y sub m be color 3. And we can swap the 2 and the 3 if we want 2 to actually be the one of those that's got the most vertices in it. So we can actually swap those two if necessary in order to get a minimum. Then by definition, the definitions that we laid out earlier, S sub min is the minimum S sub ij, which is the minimum chromatics or the minimum coloring over any chosen proper pair ij. So it is the minimum possible chromatic sum. So this just follows from definition, and the claim is then proven. And in our original graph, we can see this. K is greater than or equal to 4 because x sub 3 is the maximum subscript of color 1 x's, if you will, and y sub 2 is the maximum subscript of color 1 y vertices. So L is going to be any value greater than or equal to 3, and K is any value greater than or equal to 4. And again, x4, x5, y3, y4, and y5 make up a complete graph. So the x's and y's in that subset are going to be neighbors. They have to be different colors. In this particular case, we're going to let black be color 3 and blue be color 2 because there's more blue vertices than there are black vertices. And that's what I was saying. We can swap 3 and 2 in order to get a minimal value. So what does this proof give us, and what is it used for? In this particular paper, one focus of this paper is what's called time complexity. And this is just a computer science term for measuring, if you will, the time required to run an algorithm. How efficient is an algorithm? And you want algorithms to run as quickly as possible. And we use big O notation for that. So if a graph, if the algorithm runs in constant time, then it's a factor of 1. If it's linear time, it's a factor of some value n. If it's quadratic time, it's the factor of n square, and polynomial time is n to the k, where k is, obviously k greater than 2. So in this particular case, for a bipartite chain graph, the time complexity of the algorithm for computing the chromatic sum is the O factor of the size of the vertex set plus the size of the edge set. And there's a proof for this given following the proof that we just looked at. So in the paper, there's a proof for the minimum chromatic sum that we just looked at, and then they use that proof as part of the proof for proving that the time complexity of computing running this algorithm for a bipart chain graph is owed to the absolute value of v plus the absolute value of e, which comes out to being that's a linear time complexity. And that is the context then of how the proof that we just looked at is used in this overall paper. Thank you for watching this presentation.